So there are really only two types of problems when you look at electrolysis. The first one's not so bad, and unlike the last chapter, they're all done the same way. So it's a little bit or a lot easier. So we're going to do number 98 on page 883. And it says electrolysis of an alkaline earth metal chloride using a current of 0.5 amps for 748 seconds deposits 0.471 grams of a metal at the cathode. What is the identity of the alkaline earth metal? Okay, so let's start with writing out a generalized form of this alkaline earth metal chloride. Since it's an alkaline earth, we know it's a +2 charge on the metal, and therefore it's MnCl2. Okay. So it took 74, or they did electrolysis for 748 seconds. So 748 seconds, okay, and we start with that, and the amperage is 5 amps. So you're always going to start with the time, and then we use the amperage to convert to coulombs. What does 5 amp mean? It means that 5 coulombs pass through the wire every second. Okay, so start with the time, then use the amperage. I don't know why I put that seconds in parentheses. Gives me 5 coulombs. So we go time, then the amperage, then we use Faraday's constant. So there are 96,485 coulombs of charge in 1 mole of electrons. Okay? Then we use the equation. So we're going to use some stoichiometry. We know that to get the pure metal, we will need 2 electrons. I keep wanting to write manganese. So to get the solid metal, not the ionic form, we're going to need 2 electrons. So for every 2 moles of electrons, I'm going to get 1 mole of my metal. Okay? So these problems always follow the same pattern. Step 1, time. Step 2, amperage. Step 3, Faraday's constant. Step 4, use stoichiometry. And a lot of times this is where they ask you to end, or they tell you what the metal is, and they say, okay, the metal is copper, how many grams of copper are formed? Since you know the moles, you would just multiply by the molar mass. So my answer is 0.01938 moles. Okay? Like I said, if they told you the metal, you would just multiply it by the molar mass. But they didn't. They wanted to make this problem just a teensy-weensy bit harder. So what they said was, at the electrode, 0.471 grams of the metal appeared at the cathode. So if 0.471 grams appeared, and I have this many moles, I just divide the grams by the moles, and I get 24.3 grams per mole. Well, there's only one element that can be, and that's going to be magnesium. So that's my unknown metal. Okay? Next problem. All right, now this problem is trickier. And I'm going to compare, so they ask you what is going to be formed at the anode and what's going to be formed at the cathode when you run through electrolysis. So I'm going to say, we're going to do two problems here. We're going to do molten aluminum fluoride, and then we're going to redo the problem with aqueous aluminum fluoride. So molten aluminum fluoride means you just have aluminum and fluoride, nothing else, okay? So this one's pretty straightforward. So everything's written as a reduction. So I go to my chart, and the cell potential of this reduction is negative 1.66 volts. And then I look for the other reduction, okay? I have to have one oxidation and one reduction. So I have to flip one of these. Well, which one am I going to flip? Well, if I'm doing electrolysis, my cell potential must be negative. So what I have to do then is I'm going to have to flip the fluorine one. So this becomes boop, 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 ba-doo. Okay. Whoops, no, it doesn't become that. There we go. All right, and so the cell potential, if they're asking for it, would be negative 4.3. So it'd take that many volts to create solid aluminum. So this is my reduction. So aluminum is going to appear at the cathode. And what's going to appear at the anode? Fluorine gas, because this is my oxidation. So as you know, fluorine gas is dangerous, so that would be bad, but that's one way you could make pure aluminum, but then the fluorine gas would probably kill the person making it. All right, now what if it was in solution, aqueous? Now the problem gets a little bit trickier, all right? So if it's aqueous, it means it's in water. So we have three things present. We have aluminum ions, we have fluoride ions, and we have water. So we have three things present, okay? So we go to our reduction table on page 833, and then we look for these three things, the aluminum, the fluoride, and the water, okay? They have to be by themselves, either on the left side or the right side of the equation, okay? Left side or right side of the arrow, okay? So right off the bat, we know that we have this one, the fluorine. Okay. And I know I've got the aluminum. But now we've got water. And so if you scan down the chart, the first reaction that I see that's got water all by itself is this one. So there's water all by itself on the right side of the reaction. The fluoride up here is on the right side of the reaction. It doesn't matter if it's on the left side or the right side, but it must be by itself. Okay. I keep scanning down and scanning down and scanning down, and then I find another reaction with just water. And that produces this, okay? And I keep scanning and I keep scanning and I keep scanning, and I find another reaction with just water by itself. This one. All right. So maybe if you get really good at this, you can do this intuitively in your head. I can't. So what I try to do is say, okay, is my stuff on the correct side? So my fluoride needs to be on the other side because I don't have fluorine, I have fluoride. So I need to, when I mean I've got fluoride, I mean I have fluoride right there. I don't have fluorine. So I got to flip this equation around. All right? So I'm going to flip this equation around. Now that becomes negative 0.287. Do I have aluminum 3 plus? Yes, I do. Water. Water must be flipped around. And when I flip it, the potential flips. I'm just going to draw a line there. Okay, next one. Is the water on... Nope, it's not on the correct side, so I have to flip the water. So this becomes negative. Oh, I forgot to write my aluminum equation in there. I'll write it at the bottom. And then I am going to, this next one, I'm going to number the reactions. It probably would have helped if I would have kept them in order. But I'll number them. Well, it also would work if I actually numbered them correctly. It's 1, 2, 3, 4, 5. 1, 3, 4, 5. Okay, the fifth reaction, the water is on the correct side. So we don't have to do any flipping of that charge. I'm sorry, I forgot to write the aluminum reaction. Okay. We didn't have to flip that one. So we have to, the way I think of electrolysis in batteries is in the following way. Batteries are getting a positive potential, okay? I think of that as making money. If you're going to make money, you want to make as much money as you can. So you want to have the biggest positive potential you could possibly get, okay? If you're doing electrolysis, you're losing money. So if you're going to lose money, you want to lose the smallest possible amount of money you can, okay? So you need to have a reduction, you need to have an oxidation. So let's first look at the reductions because they're right next to each other, so maybe it was a lucky coincidence. So here are the two reductions. Okay? Those are the two reductions. Which one's smaller? Equation number, whoops. Here's my two reductions. Which one is smaller? This one is smaller. It's got a point, negative 0.8. What would you rather lose, $80 or $166? Okay, so negative 0.8 is a smaller loss. So that's why that one is picked. Okay. Now let's look at our oxidations. Here are our oxidations. Okay. So which one of those causes us to lose the least amount of money? This one, negative 0.123. So even though our solution is aluminum fluoride, what's happening at the anode and the cathode are reactions 4 and 5. So remember that if this is my reduction, this is going to be occurring at the cathode. So at the cathode, guess what gas is being produced? Hydrogen. This is my oxidation, so guess what gas is being produced at the anode? Oxygen. So this is a typical problem they'll ask you, and it throws people off because they automatically think that something's got to be involved with the aluminum and the fluorine. Okay? One final problem. It'll go quicker, I assure you. Selective precipitation of ions. Okay? So suppose that we've got the following metals in solution: copper chloride, nickel chloride, and then tin chloride. Okay? So we want to find out which one of these will be plated out first. Which one will turn solid first? So here are what we have. We've got copper ions, we've got nickel ions, we've got tin ions, and we and don't forget we've got water present and we have chloride. All right, so we have to do the exact same thing as we did before. All right, so first let's write all the reactions down. So copper is 0.34, nickel is negative 0.23, and we've got zinc at negative 0.76. So we're not going to have to flip those three reactions at all. I'm going to call them reactions 1, 2, 3. Then we remember we've got chloride. So I see chlorine, the chlorine reduction right here. But we don't have chlorine, we've got chloride, so we have to flip it because the chloride is on the wrong side. And then the charge flips. Okay? And then we've got water. And so we got to go back to those water reactions. I'm not going to include the one with hydrogen peroxide because I know it's wrong. Not going to be the correct answer, and I want to minimize. So the two that are most common, so we've got this one, O2 plus 4H plus 4 electrons, yielding 2 H2Os, 1.23. The water is on the wrong side, so I have to flip it. That becomes negative. And then my other water equation is down here. All right. So that one is written correctly. The water is already on the right side. So I have to pick a reduction and I have to pick an oxidation. So looking at my oxidations, I'm looking at equations number 4 and number 5. Okay? So those are my only possible oxidations. So thankfully, number 5 is smaller than number 4. The reason why I say thankfully is because by doing number 5, I'm going to be producing oxygen gas. If I was using number 4, I'd be producing chlorine gas and people would be dying. And I don't want to produce chlorine gas. But again, if you don't know what you're doing, you'll see little bubbles. You know, I mean, sometimes people do produce bad gases when they're doing electrolysis and they don't realize it, and they're actually producing and then they inhale it. So you should know what you're doing. So you want to have the smallest loss. So that's why we're picking the equation number 5 for my oxidation. Now what about my reduction? So again, you want the smallest possible negative number. Okay? So here is the order of electrolysis. Which of the remaining reactions will give you the smallest negative number? Reaction 1. So what's going to happen is you are going to plate out the copper first. Okay? So at the oxidation, there's my anode, and this is going to happen at the cathode. Okay? So on my cathode, I am going to get a layer of copper that's going to plate onto my electrode. So the electrode is going to get heavier. Once all the copper ions have been taken out of solution, then which one will give me the next smallest cell potential, the next smallest negative number? The nickel. So then the nickel will start to plate over the copper. Okay? And then which one will give me the next smallest potential? Number 3. Actually, let me calculate this out. So I would need So to plate out the copper, I would need negative 0.89 volts. So I'm gonna make a category over here. So negative 0.89 volts to plate out the copper. To plate out the nickel, I would need negative 1.46 volts to plate out the nickel. To plate out the zinc, I would need a voltage of 1.99. And the zinc will start to plate over the... So sometimes electrolysis isn't great if you've got a lot of mixed ions, because you don't know when all the copper's gone, and the next thing you know, you've got nickel covering up your copper, and you don't always know when all the nickel's gone, and the next thing you know, you've got zinc covering up your nickel, covering up your copper. However, this is a very effective way if you want to apply a very thin layer of a metal over another substance to protect it. So a lot of times they will put a thin layer of zinc over iron to protect it so the iron doesn't corrode. And if we were to continue to do electrolysis, eventually we would have reaction number 6, and the water would start to I wrote that wrong. There we go. Then the hydrogen gas would start to build up, and then you know you have all three out. So that's one question. By the way, would I be able to plate out aluminum if aluminum was in this solution? Suppose I had aluminum chloride. Would I be able to plate out the aluminum chloride? And the answer is no, because aluminum and this is why it's so difficult, is negative 1.66 volts. So the aluminum has got a greater negative potential than equation number 6. So after the zinc gets plated, you'd spend the rest of your time reducing the water. So you'd have to reduce all the water away before you could begin to possibly reduce the aluminum. So that's why this would not plate out any aluminum.